Hello and welcome to Stories of Science. Here, we look back on humanity's long journey to understand the world. The questions, the failures, and the breakthroughs that slowly changed how we see the universe and ourselves. We tell science as stories.
Neptune, the planet that should be dead, but isn't. The night sky looks calm, almost polite, like the universe has clocked out for the day. Especially out at the edge of the solar system. It feels empty, cold, still. As if nothing interesting ever happens there. But that's the trap. Because if you think that region is quiet, you're seriously underestimating it. Wind speeds there can hit over 2,000 kilometers per hour. That's not a breeze. That's a planetary blender. Clouds don't drift. They get launched. Storms are so huge they could swallow Earth whole, and all of this happens with barely any sunlight. So the obvious question is, what's powering this madness? And why is a frozen world acting so aggressively alive? Here's where it gets even better. We didn't even see it first. We calculated it. Back in the 1800s, astronomers noticed something weird about Uranus. Its orbit wasn't behaving at tiny deviations. But in space, nothing is ever just a tiny thing. Because gravity doesn't lie, something had to be pulling it. And as the saying goes, the devil is in the details. So one French mathematician started working backwards. No computers, no simulations, just paper, ink, and Newton's laws. He basically tried to solve for the unseen planet. Adjusting mass, distance, angle, again and again, like assembling a puzzle with no picture on the box. At the same time, another scientist in England was doing the same thing, different country. Same conclusion forming. They weren't observing the sky anymore, they were interrogating the data. Eventually, a prediction was made down to a specific patch of sky. Astronomers in Berlin pointed a telescope there, and almost instantly, there it was. A blue world that wasn't supposed to exist in that exact spot. That moment changed everything. It was the first time humanity found a planet through math first, and eyesight second, like predicting rain with equations, and then watching the sky agree. But the story didn't stop there. Because this calm ice giant turned out to be anything but calm. Voyager 2 later flew past it in 1989, and what it saw was wild. Winds faster than anything on Earth, storm systems behaving like engines with no off switch. If you stood in that atmosphere, you wouldn't say nice weather. You'd be gone before finishing the sentence. And the strange part? It shouldn't even have that kind of energy. It's too far from the sun, too little sunlight, too little input. And yet the whole planet is running like a storm machine that refuses to shut down. As people say, where there's smoke, there's fire, but here, there's wind without a clear flame at all. Even today, we're still piecing it together. A world first predicted on paper, then confirmed by a telescope, then revealed to be far more violent than anyone expected. Maybe that's the real lesson. We don't just discover the universe sometimes, we solve it first, and only later realize what we were even looking at. By the time Voyager 2 reached Neptune, humanity had already been mentally rehearsing that moment for decades. We had calculated it into existence. We had inferred its mass from orbital wobble. We had even named it in textbooks before we ever saw it. But here's the catch. Knowing something, and seeing it, are completely different games. In August 1989, Voyager 2 finally entered Neptune's neighborhood. At that point, it wasn't just a spacecraft anymore. It was a 12-year-old veteran, limping through the outer solar system. Jupiter, Saturn, Uranus, check, check, check. Old, tired, low on power, but still doing its job. One last stop, as they say, and that stop was Neptune. As the distance closed to a few million kilometers, scientists got unusually tense. Not because something might go wrong, but because nobody actually knew what was waiting. Everything before that was Earth-based guessing. A blue dot, a blur, a rumor with gravity. Then came the first close-up images. And Neptune immediately stopped behaving like an idea. The first shot was a storm. A dark oval system bigger than Earth itself, later nicknamed the Great Dark Spot. You could literally drop Earth inside it, and still have room left over. But here's the strange part, it wasn't stable. It moved. It changed. It disappeared. Like a storm that refused to stay in the script. And then Voyager 2 found something even more bizarre. fast-moving cloud bands racing through the atmosphere. So fast scientists casually called them scooter clouds. Because that's what they looked like, clouds on a joyride. If Earth weather worked like that, a cloud could circle the planet in about an hour. Just think about that for a second. As the saying goes, slow and steady wins the race, but not here. Nothing about Neptune is slow. Then came the closest encounter. About 4,800 kilometers above the cloud tops. On a planetary scale, that's basically a near miss. Close enough to see structure inside the atmosphere, close enough to realize something important. Neptune wasn't a quiet blue marble. It was a moving machine, and it was loud in all the ways that matter. Back on Earth, the data caused a kind of scientific reset. We thought Neptune would be cold, stable, almost asleep. Instead, Voyager 2 saw storms, jet streams, shifting systems, constant motion. One scientist summed it up with brutal honesty. We expected an ice ball. We found a cosmic hairdryer. A joke, but also uncomfortably accurate. Because somehow, this distant world runs some of the fastest winds in the entire solar system, and nobody fully knows why. Then comes the part that makes it even more surreal. Voyager 2 is still the only spacecraft to ever visit it up close. No second flyby. No backup mission. Nothing. So our clearest memory of Neptune is still that one brief encounter in 1989. A single pass. A snapshot. A cosmic drive-by. And as Voyager 2 drifted away, another set of numbers quietly reframed everything. Neptune sits about 4.5 billion kilometers from the sun. Sunlight takes nearly 4 hours to reach it. So if Neptune could look back, it would see the sun, 4 hours in the past. Its year? 164.8 Earth years. 1 lifetime wouldn't even finish a single orbit. Its size? 4 times Earth's diameter, but volume-wise, you could fit about 64 Earths inside. And its mass? 17 Earths. Yet it's not a solid super-Earth. It's a deep, high-pressure, fluid world wrapped in violent atmosphere. A place where intuition stops working. As the saying goes, don't judge a book by its cover. Neptune takes that personally. Because nothing about it fits the way Earth-trained instincts expect. And maybe that's the final lesson Voyager 2 left us with. We didn't really see Neptune. We just passed by it, and caught a glimpse. When Voyager 2 sent back the first close-up images of Neptune, scientists noticed something immediately. It was blue, and not just nice ocean blue. This was a deep, almost unreal kind of blue, the kind that looks like someone turned the saturation slider all the way up and said, "Good enough." But this wasn't Photoshop. At least, not at first. The main reason is methane. Neptune's atmosphere is mostly hydrogen and helium, but methane, though relatively small in amount, does something very powerful visually. It absorbs red light from the sun. So the red gets filtered out. What's left gets scattered back, blues, a bit of green. And that's what reaches our eyes. Simple enough, on paper. But here's where it gets tricky. Uranus also has methane, yet it looks more pale blue-green, almost washed out compared to Neptune. So clearly, methane isn't the whole story. As the saying goes, the devil is in the details. Later studies, especially with Hubble data, showed something deeper. Neptune's atmosphere is more transparent in a way that matters. Sunlight penetrates deeper before bouncing back. And deeper layers mean more red light gets stripped away. So what returns is a purer blue signal. But there's another twist most people don't realize. Many of the iconic Voyager 2 images you've seen, they're not exactly raw color. Scientists enhanced contrast and adjusted color balance not to mislead, but because the raw data was too dark to read clearly. So what we remember as Neptune's deep blue is partly science, partly image processing, or as someone joked, the most photogenic planet in the solar system. If you strip all that away, Neptune might actually be closer to a softer blue-green tone, less dramatic, more subtle, still alien. But either way, one thing is certain. You look at it, and you know this is not an ordinary planet. And once the color mystery settled, Voyager 2 hit science with something even more chaotic: the weather. Neptune doesn't just have wind. It has extremes. Measured wind speeds go beyond 2,000 kilometers per hour. For comparison, Earth's strongest hurricanes top out around 300 to 400. So Neptune isn't just faster. It's in a different league entirely. As the saying goes, you can't compare apples and oranges, and you definitely can't compare Earth storms to this. On Neptune, wind isn't something you feel. It's something that happens to you. Before you even process it, you've already been moved somewhere else. One of Voyager 2's most famous discoveries was the Great Dark Spot, a storm roughly the size of Earth itself. Huge, clean-edged, almost elegant in its violence. But it didn't behave like Jupiter's storms. It moved, it changed, and eventually, it disappeared. Later, when Hubble looked again, it was gone. Just gone. Like someone turned off a weather system. And somewhere else, new storms appeared. This confused scientists deeply, because Jupiter's Great Red Spot can last centuries. Neptune's storms don't stay. They form, evolve, vanish, repeat. Not a stable system, more like a constantly rebooting atmosphere. Then there were the so-called scooter clouds. Fast-moving cloud streaks racing across the planet. Scientists gave them a casual name, but the behavior is anything but casual. These clouds move so fast they look like they're being pulled rather than drifting. If you slowed time down, Neptune's sky wouldn't look like weather at all. It would look like a fluid in constant conflict with itself. A machine that never stops stirring. But here's the real puzzle. Neptune gets about 1/900 of the sunlight Earth receives. That's barely anything. So where does the energy for all this chaos come from? It shouldn't have enough power to drive winds like this. And yet it does. So the question becomes deeper. If not the sun, what is powering Neptune's atmosphere? Even today, there's no complete answer. And maybe that's why Neptune is so fascinating. It looks like it should be quiet, frozen, simple, but it behaves like a system that refuses to follow expectations. Blue, stormy, unstable, alive, and as the saying goes, still waters run deep. Neptune takes that idea and turns it into a planet. As scientists continued peeling back Neptune's blue storm machine, a more uncomfortable question started to emerge. If the outside is already this chaotic, what's going on inside? For a long time, the standard idea of outer planets was simple: the farther you go from the sun, the colder things get, the more frozen everything becomes. So early on, Neptune was imagined as an enormous ice ball. A frozen world. Quiet, stable, almost like a cosmic freezer left running in the dark. But Voyager 2 didn't agree with that picture. And as more data came in from Voyager, Hubble, and modern interior models, the old idea started falling apart. Neptune isn't an ice ball. It's more like a layered pressure system, constantly compressing itself under its own weight. In simple terms, it has three main layers: a hydrogen-helium atmosphere on top, a so-called ice mantle in the middle, and a rocky core at the center. Sounds neat, clean, organized. But the problem is that middle layer. Because ice there has almost nothing in common with ice on Earth. Here, ice means frozen water. Solid. Familiar. Inside Neptune, pressure climbs to millions, even tens of millions of times Earth's atmosphere. And under that kind of stress, water, ammonia, methane, they stop behaving normally. They enter a strange state, supercritical fluid. Not quite liquid. Not quite gas. Something in between, constantly shifting. As the saying goes, things are not always what they seem. And if you force an Earth analogy, you end up with something almost absurd: a planet-sized pressure cooker, endlessly stirred at extreme temperature. But this isn't static. Far from it. Models suggest this ice mantle is slowly convecting as heat rises, material moves, everything circulates under immense pressure. Slow here is misleading. On a planetary scale, it's still a massive energy engine. Deeper down sits the rocky core of silicate and metal, more familiar territory. But even that isn't calm. Above it, thousands of kilometers of high-pressure fluid constantly squeeze it from all sides. So it's not a stable center. It's more like a compressed engine trapped inside a crushing shell. Put all of this together, and Neptune stops looking like a neatly layered planet. It looks more like a gradient of matter, gas becoming fluid, becoming something almost solid, all under extreme conditions. And that leads to a strange realization. If you fell into Neptune, you wouldn't hit a surface, you wouldn't splash like water. You'd transition: gas, then dense gas, then supercritical fluid, then extreme compression. No landing, no stopping point, just gradual transformation. As the saying goes, you can't step into the same river twice. On Neptune, you can't even stay the same matter twice. Naturally, scientists started asking a bigger question. Is Neptune even a solid planet at all, or is it closer to a fluid system held together by gravity? Increasingly, the answer leans toward the second. And just as that idea was settling in, Voyager 2 delivered another curveball: the magnetic field. On paper, a planet with a conducting interior should produce something like Earth's magnetic field. Neptune doesn't. First, its magnetic axis is tilted about 47 degrees. Imagine a bar magnet stuck inside a planet but crooked, badly aligned. Even stranger, the magnetic field doesn't originate from the center. It's offset. That's highly unusual, because most planetary magnetic fields are generated by internal convection around a central core. Neptune breaks that symmetry completely. It's like a generator that was installed slightly off-center, and nobody fixed it. The result shows up in its auroras too. On Earth, auroras form fairly stable rings near the poles. On Neptune, they're scattered, shifted, unpredictable. Like the magnetic field is sketching in the dark without a plan. As the saying goes, a broken compass still points somewhere, but Neptune's compass doesn't even agree on where the center is. Compared to Earth's tidy system or Jupiter's powerful but structured magnetism, Neptune feels improvised. And that's what makes it so important scientifically. It doesn't fit the textbook model. It challenges it. When you combine everything we've learned, a picture starts to form. A violent outer atmosphere, a supercritical middle layer, a compressed rocky core, and a tilted, offset magnetic field. Neptune isn't a standard planet. It's a physical system pushed to extremes, still moving, still evolving, still trying to find balance, but never quite settling down. If you step back from Neptune's chaotic interior and look outward, something unexpected shows up. It's not just a storm machine, not just a pressure system. It actually has decorations. Yes, Neptune wears rings, and they don't behave the way you'd expect. Astronomers first suspected them in the 1980s from Earth-based observations. Then Voyager 2, in 1989, finally confirmed them up close. But unlike Saturn's clean, textbook-perfect rings, Neptune's system looks unfinished. Almost like someone started drawing circles and forgot to finish the job. Its main rings like Gal, Leverrier, and Lassell exist, sure. But the real oddity is the broken structure: arc-shaped segments instead of full circles. Gaps, pieces, fragments of rings. As the saying goes, nothing in life is perfectly round. Some of these arcs even have names like liberty, equality, and fraternity. Yes, French astronomers basically imported a revolution into space naming conventions. So you end up with a bizarre image 45 billion kilometers away, parts of rings floating in space carrying political slogans. Beautiful, strange, very human. But science had a problem to solve. Why aren't these rings complete? Physics says they should smooth out over time into stable circles under gravity. But Neptune's rings don't cooperate. One explanation is shepherd moons. Small nearby moons constantly tug on the ring particles, shaping them into arcs instead of letting them spread evenly. So it's not that the circle can't form, it's that something keeps erasing parts of it. Add solar wind, micrometeor impacts, and you get a system that is constantly shifting. In other words, what you see today might not exist the same way tomorrow. As the saying goes, change is the only constant. And just when the ring system starts to feel elegant but unstable, you move outward again and meet something completely different. Triton, Neptune's most famous moon, and also its most suspicious guest. Because Triton moves the wrong way. It orbits in retrograde, meaning it goes against Neptune's rotation. In planetary science, that's usually a red flag. It almost always means it didn't form there. Most evidence suggests Triton was captured from the Kuiper Belt, a distant reservoir of icy bodies. In simple terms, it wasn't born here. It was taken in. And that capture wasn't peaceful. Models suggest a violent gravitational interaction, possibly disrupting or reshaping Neptune's original moon system. So Triton didn't just arrive. It rewrote the neighborhood. And it's still unusual today. Voyager 2 found it to be one of the coldest objects ever measured, around -235 degrees Celsius. Cold enough to freeze nitrogen, methane, almost everything. But it's not dead. On its surface, Voyager saw something shocking: cryovolcanoes. Ice volcanoes. Instead of lava, they erupt nitrogen, methane, and icy slurries. Then it all freezes back onto the surface. A world that erupts ice sounds like science fiction, but it's real. And its terrain, smooth plains mixed with strange textured regions, suggests it may still be active. Not frozen in time, just very, very slow. But the real tension comes from its orbit. Because Triton is on borrowed time. Its retrograde motion means it's slowly losing energy over geological timescales. Far in the future, it could crash into Neptune, break apart, or shift into a new orbital state. It doesn't look permanent. As the saying goes, nothing lasts forever. Triton feels less like a native moon, and more like a long-term visitor who overstayed. When you put everything together, the picture gets stranger. Broken but elegant rings. A captured, backwards moving moon. A system still shaped by ancient chaos. Neptune stops looking like a calm outer planet. It starts looking like a system that survived something violent, and is still settling down. And that realization pushes us deeper. Because Neptune is too far, too cold, and too starved of sunlight to make sense in a simple way. By basic physics, it should be almost inactive. A cold object with very little energy input. But Voyager 2 and later observations showed something surprising. Neptune is still leaking heat. In fact, it emits about twice as much energy as it receives from the sun. That shouldn't be happening. So where does the extra energy come from? There are a few theories. One is leftover heat from formation, gravitational compression during its birth, but over billions of years, that should have mostly faded. Another is internal convection inside its deep ice mantle, where supercritical water, ammonia, and methane slowly circulate, transporting heat upward. But how efficient that process is still debated. A third idea involves tidal heating from Triton's gravitational pull, gently flexing Neptune's interior. But even that may not fully account for the numbers. So we end up with an uncomfortable truth. We know Neptune is warm inside, we just don't fully know why. And that makes it oddly compelling. It behaves like a system that shouldn't still be on, yet clearly is. As the saying goes, the machine keeps running even when no one is watching. Which also explains why we haven't gone back. Since Voyager 2, no spacecraft has visited Neptune up close. Not because it's unimportant, but because it's extremely hard. 45 billion kilometers away is not just far. It's an engineering wall. Even the fastest probes would take over a decade to get there. And solar power barely works at that distance, so missions need nuclear power systems, which are expensive and limited. Then there's the communication delay, about 4 hours one way. You don't control a spacecraft there. You wait for it to answer. And finally, there's funding reality. In space exploration, priority matters. Mars is closer. Jupiter is richer in data. Saturn already has legacy missions. Neptune ends up in the category of someday. But not forgotten. Because proposed missions, orbiter concepts, atmospheric probes keep appearing in long-term plans. Just not yet. And when you zoom out, Neptune becomes more than a single planet. It becomes a reference point. A cold, distant, still active ice giant that challenges every simple model we build. And that leads to an uncomfortable thought. Are we really understanding Neptune? Or are we just learning how to describe fragments of it? Because from Voyager 2 to today, one thing remains consistent. Neptune is still moving, is still active, still not fully explained.
The people who change the world usually just think one step deeper. If this story made you see things differently, hit like, subscribe, and save it. See you in the next story.